Hello everyone. In this lesson we're going to take a look at how fusion and gravity both play a major role in the life of a low to medium mass star. And these two forces are in a constant struggle with each other, trying to either collapse the star or explode the star. So there's this constant struggle between gravity, and gravity is an attractive force that pulls all matter together. It's trying to crush the star as small as it possibly can. And then there's fusion, which is generating lots of heat, lots of energy, and that energy is trying to expand, right? It makes those particles move faster and spread out. So there's this pressure trying to push the star apart from the nuclear fusion, and there's gravity trying to collapse it together. Now we want to get a little bit closer into how gravity works, because it is an attractive force that pulls all particles with mass together, and you guys are familiar with it. You have mass, and gravity keeps you stuck to the surface of the Earth. You jump, you fall back down. But it's a little bit more complicated than that. Gravity's strength depends on two quantities. It depends on the masses of the objects that are attracting to each other, and it depends on the distance between them. The bigger the mass, the stronger the strength of attraction between the two objects. So even though we're 98 million miles from the sun, the Earth's mass combined with the sun's mass means there's a pretty strong force of attraction between those two bodies. And if we were even closer together, there would be an even stronger attraction, because the distance between particles also matters. So increasing mass increases the strength of gravity, which means that's a direct relationship. But decreasing distance increases the strength of gravity, and that means that's an inverse relationship. But it's actually an inverse square relationship. Remember, squaring something means that you multiply it by itself, and inverting something means flipping it over. So if we cut the distance in half, right, that's distance, then to figure out how much the force of gravity is affected, we have to invert that half, so 1 over 2 becomes 2 over 1, and then we square it, and 2 squared is 4, and 1 is squared is 1, so that becomes 4 over 1, or just 4. So we get 4 times as much pull, or 4 times the gravitational strength, as particles get half the distance between them. So we cut the distance in half, 4 times as much force. And that plays a major role in stars, because what happens is we have this cloud of hydrogen gas floating out around in a spot in space, and it might get perturbed by, say, explosion of a star somewhere else, gravitational wave, whatever, but this hydrogen cloud starts to collapse, and as the particles get closer to each other, the gravity gets stronger, and it pulls in more particles, and that means more mass, and that means more gravity, and that pulls things in closer together, and that means more mass, and that means more gravity. So gravity continues to get stronger and stronger and stronger and stronger and stronger, and that means that all of a sudden these particles are smashing into each other pretty hard and a lot. So we get lots of collisions happening, and when the particles collide and start bouncing around like that, that creates lots and lots of heat. And so we start getting this little glow from this heat, and gravity continues to pull things together and collapse this gas cloud, and it starts getting warmer, and it's glowing, and all of a sudden it gets so hot that we don't actually have atoms of hydrogen anymore. The electrons get stripped off of the protons, right? A hydrogen atom is just a proton and an electron. And so now we've got plasma. We've got the plasma state of matter, and gravity continues to contract this thing, and it's getting really hot, it's glowing, and then it gets so hot that the protons are able to reach that magic distance where the strong nuclear force overtakes them, and they come together and nuclear fusion begins. So we go from this glowing ball of gas called a protostar to a main sequence star. Once we start fusing hydrogen into helium, we have what's called a main sequence star, and this is a very efficient process. So the fuel, the hydrogen, is being burned. It's not really burned, but we call it burned. It's not oxidizing with oxygen, but it's fusing into helium. It's efficient, it produces lots of energy, and so the pressure from this energy being released is able to balance gravity, and the star is pretty stable, and it can stay like this for millions and millions of years, just happily fusing hydrogen into helium. But eventually we're going to run out of hydrogen. At least we're going to run out of hydrogen in the core, right? The fusion is turning all that hydrogen into helium, and the helium, well, helium is big, right? It's 2 protons. It's got twice as many protons as hydrogen has. It's got 2 neutrons. It's bigger, it's heavier, it's much, much harder to fuse helium together. It takes a whole lot more energy to get those 2 nuclei together. And when they do fuse together, it doesn't release as much energy as it did when 2 hydrogen nuclei fuse together. So the star is going to have a problem. Eventually the core is going to run out of hydrogen, and nuclear fusion is going to stop in the core. That doesn't really mean it's the end of the road for the star yet, because that means gravity can continue to contract that core and make it smaller, right? Because the pressure in there is gone now, right? There's no nuclear fusion creating that pressure, but around that core is still really, really hot, and there's still hydrogen around that core. So what we see here is this hydrogen burning shell. So fusion is still happening there. There's still going to be an outward pressure, but that means that this star is going to start getting bigger, right? Because now this pressure is outside the core, and the gravitational pull inside the core is affecting this less and less as this particles get further and further away. So the star actually expands, and we get what's called a red giant out of this. And so we ran out of hydrogen in the core, but helium is still being produced outside the core, as hydrogen outside the core is fusing. Gravity is collapsing the core, and the outer layers are fusing hydrogen. The star becomes a red giant, and eventually the core gets really, really, really hot again. And that means we can start fusing helium into heavier elements. So the helium starts to fuse, and out of that we get carbon and oxygen, and that's what's this showing. But a low mass star is never going to be able to have enough gravity to crush carbon and oxygen close enough together to make them hot enough to fuse heavier elements. It's not going to happen. So this core, once it forms, that's the beginning of the end for the star. We're going to get the process to repeat with helium that happened with hydrogen. The helium in the core runs out, fusion in the core stops, gravity contracts that core together. It's still really, really hot. It's just not hot enough for fusion to occur. But the outer layer, right, that's where helium is still at. We can still have helium happening there, helium fusing there into those heavier elements, which will continue to get dumped into the core. And that's going to cause another expansion. This expansion is so violent, though, and so big and so far from the core that actually the outer layers of the star stop being held onto the star. And we get this cool looking thing in space called a planetary nebula. And that's what this image shows. You can see in the center of that you have the hot, super white hot core of that star, and it's surrounded by this glowing ionized gas. That gas is being ejected. It got so hot that it got pushed away. This core is so small now, gravity's contracted it in, that it can't hold on to all of the mass anymore. And this is basically the beginning. This is where the star stops being actually a star anymore, because it's no longer carrying out fusion. From here on out, it's just glowing with residual heat. And it'll glow for a while, but that white hot core, called a white dwarf, is eventually going to fade out, and that white dwarf is going to become a black dwarf, and then, well, we can't see it anymore. It's not producing light. So it's a main sequence when it's fusing hydrogen into helium. It becomes a red giant when it's fusing helium into other things, and then it runs out of fuel. It can't go past fusing helium, and it's going to fade out. Now, there's a diagram that kind of helps us put some of this together, and this is called an HR diagram. It's named for two guys, Hertzsprung-Russell, who came up with it. And all it does is it orders the stars by luminosity. That's how bright it is. And you can see this is really, really bright, and this is fairly dim. And temperature, and it's hot over here. You got to remember, hot goes with blue. Blue is higher energy, and red, this is fairly cool. And you can see this line right here of all these stars. These are main sequence stars. They are happily fusing hydrogen into helium. It's outside of this line where the cool stuff is happening, where the stars are ending their lives. And so our sun is a low to medium mass star, and eventually it's going to jump out into this giant stage, and it'll work its way back over and cool off. And we're going to look at how that happens actually on the next slide. But an HR diagram, it is showing the luminosity of stars versus the temperature, and how these stars move around on here as their life goes on. So let's take a look at how the diagram changes as the star progresses through its life. So hydrogen fusing in the core stops, and then hydrogen fusing in the shell causes that thing to expand, turn into a red giant. Then helium fusion in the core causes it to get hot. Then helium fusion in the shell causes it to expand again. It ejects its outer layers. Now we just have the hot, bright core left, and then that cools and fades. So what we have going on here is right here it exits the main sequence, and so hydrogen fusion stops. And then that means we have hydrogen fusing in layers. And so it expands and cools. expand, and cools. And it's this expansion that makes it bright because now it's bigger, so it's got more light coming out of it, but it also makes it cool because those outer layers are further from the heat, so the surface of it is cooler than if it was a smaller star. And then we have helium fusion starting. So helium fusion starts, and this is in the core. And that causes this thing to actually get very hot again. So now it's hot, and then helium in the core stops. So helium fusion in layers is going on right here, and again that causes it to expand and cool, but it also makes it bright. So you'll notice this thing has been getting progressively brighter. It's getting brighter because it's getting bigger, and then it gets hotter, and then it gets bigger and brighter, and then it ejects the layers, and that leaves just the very, very, very hot core, and that hot core then cools off and fades to a white dwarf. So as this thing is moving through these stages, what we really have is it enters the giant stage, and then the planetary nebula stage, and then the white dwarf stage.